Now that we know about intraparticle and interparticle forces, and we understand a little bit about how electronegativity affects polarity, we're going to talk about those intra and interparticle forces in more detail. We're going to talk about the 7 different forces that are commonly found in chemical structures and chemical compounds and interactions that they have, both within the particle and between 2 separate particles. The questions we'll be looking at will be focused on each of those 2 types of interactions, the intraparticle and the interparticle forces. We'll start by listing out what the 7 intra and interparticle forces are, and these are going to be listed in order of decreasing strengths. So we have a covalent bond, an ionic bond, an ion-dipole interaction, a hydrogen bond, dipole-dipole interactions, dipole-induced dipole interactions, and finally London forces, sometimes called dispersion forces. And again, these are listed in decreasing strength, so the strongest bond we have is the covalent bond, and the weakest are the London dispersion forces. These are a range of different forces, so within each one there are some that are a little bit stronger and some that are a little bit weaker within each section. But we're going to talk about which ones do we consider to be intraparticle and which ones do we consider to be interparticle. So the intraparticle ones are the ones you already know. Those are your covalent bonds and your ionic bonds. How do you know if something's covalent or ionic? Well, let's look into that next. The ones that are interparticle are the lower ones. So the ion-dipole, the hydrogen bond, the dipole-dipole, the dipole-induced dipole, and the London forces. Those are all interparticle. That means that they're between 2 separate particles, whereas the intraparticle ones were within a single compound. So let's focus on the covalent and ionic bond first. As you should already know, a covalent bond is a chemical bond that arises from the sharing of electrons between 2 atoms. How do we know something has a covalent bond? Well, this is going to be a substance that is made up of all nonmetals. As long as there's nonmetals present and no metals, then we know that we have a covalent bond present as the type of intraparticle force. If we do have a metal or ammonium, we know that we have an ionic bond. Now, an ionic bond is a chemical bond that results from an electronic attraction between the ions of opposite charge. So these are charged species. They are ions that are present. Those ions are made of a metal and a nonmetal, or a metal and a group of nonmetals known as our polyatomic ions, or possibly the one positively charged polyatomic ion that we have, and joining that with a nonmetal ion or another polyatomic anion. So again, these are the only 2 that we're going to consider in this course, intraparticle forces. And you should already be able to identify one from the other. Now let's talk about the interparticle forces. Recall that when we talk about interparticle forces, we're talking about an interaction between 2 separate species. Interestingly, those 2 species could be the same type of particle, or they could be different from each other. So for instance, I could have 2 waters joining to each other, and that would still be an interparticle interaction, even though they're both water. When I ask you questions about the interparticle forces, I'm going to ask you which is the strongest force present. In general, every particle has the lower forces present. So everything has London dispersion forces. But something that has a dipole-induced dipole force as its strongest interparticle force will not have anything above it, but will have London forces present. So when I ask the questions, it'll always ask you, what is the strongest force present? In your mastering homework, sometimes you will see a question that says, which forces are present? Then you would click everything below the one that I'm mentioning as the strongest force. So that means you need to know the order of these forces. So again, we're going to start with ion-dipole, then hydrogen bond, then dipole-dipole, then dipole-induced dipole, and finally London dispersion forces. We're going to talk about how we can identify which ones are present in each case. And again, recall, I'm going to only talk about the one that is the strongest one, as I'm talking about them, I'm not going to talk about the lower leveled ones as I go through them, but do recall that they will always be there as one of the forces present. At the end of this section, I will be asking you some questions to give you an idea of what the questions will be like. So in order to do that, you will need to know electronegativity, polarity, whether something is ionic or molecular. All of those things that we've learned previously will come into play, and then you'll need to know how to rank the strength of the interparticle forces. So let's get to it. We'll start off with the strongest one, which is the ion-dipole interaction. An ion-dipole interaction is an attraction between the partially charged end of a polar molecule and the oppositely charged ion. For this type of interaction, you need to have something that is ionic and something that is polar. And that is described in its name. It says ion dipole. So the ion part of its name tells you there needs to be something ionic. The part that says it's polar is the word dipole. So we can easily identify mixtures, interactions that are ion dipole because they have both an ionic compound and a polar compound present. And that's going to be the way that you identify an ion-dipole interaction as the strongest interparticle interaction present, is by finding both an ionic compound and a polar compound. We're going to model a simple ionic compound with a circle with a positive charge and a circle with a negative charge to show that that is an ionic compound. And when we model a dipolar compound, we're saying that it's a polar compound, we're going to make this oval shape. We're going to put a positive on one end and a negative on the other. That's to show you the types of bonds that we have. So remember that a dipolar or polar compound is always a covalent compound which has shared electrons. When we're looking at this, could this be a pure substance, so the same thing interacting with itself? In this case, it cannot be. It must be a mixture because one of the two compounds is ionic and the other one is polar covalent. And no substance can both be ionic and polar covalent at the same time. It has to be one or the other. And so we know that this has to be a mixture of two different compounds that we're looking at. So let's look at what happens when these two types of compounds mix with each other. We're going to draw an ion, and around that, I'm going to put the positive charge in this one. Around that, we're going to put a whole bunch of little circle ovals, and all of those ovals are going to have the negative charge closest to the positive charge on the inside, and then we're going to have the positive charges sticking out. And over here, we're going to draw that negative charge. We're going to put those ovals around it, and we're going to see the same thing, but now, since we have a negative charge in the middle, all the positive parts of the polar compound will be on the inside, and all the negative parts will be on the outside. Now notice that the positive from this side and the negative over here still interact with each other. So there's still interactions between those things. Those are not ion-dipole interactions, but what we do see is some really nice ion with a polar substance, ion-dipole interactions. Notice that these are very strong interactions. What we know is this is something that allows something like water to dissolve something like salt because they are strong interactions that are available to help these two things bond together, and that means that they mix very, very well. So an ion-dipole interaction allows things like salt to dissolve in water. Now, not every ion and dipole will interact with each other, so sometimes we see that some substances are not soluble in water. They don't dissolve in water, even though they're ionic. And that, again, is because of the different strengths of those interactions. Generally speaking, though, an ion-dipole is the strongest interparticle force that you can see between two different substances. One of them must be ionic and the other one must be polar for this to happen. Later, when we look at the rest of these, you'll notice, though, that this is the only type of interparticle interaction that something that is ionic has. So we only have ion-dipole, and what that means is it should be very easy to identify which combinations will have an ion-dipole interaction. If you have an ionic compound, the strongest interparticle force it could ever have, and the only one it really does have, is the ion-dipole interaction. All of the other lower ones will be available, they just won't be between the ionic compound and the polar compound. They'll be through different species, like the two polar compounds. So while the other ones are available, they won't be between the ionic compound and the polar compound. The only interparticle interaction or force that an ionic compound will have is an ion-dipole interaction. The next strongest interparticle force that's present is the hydrogen bond. A hydrogen bond is found in molecules in which hydrogen is covalently bonded to one of the highly electronegative atoms, nitrogen, oxygen, or fluorine. I like to say fluorine, oxygen, or nitrogen. And the partially positive hydrogen in that molecule is attracted to another oxygen, nitrogen, or fluorine in another molecule. Again, this is between two separate molecules. I'd like to come back to this one after I've talked about the dipole-dipole, and that'll be to show you the difference between the hydrogen bond and the dipole-dipole interactions. And our third strongest interparticle force is called the dipole-dipole interaction. This is an attraction between the partially positive end of one polar molecule and the partially negative end of another polar molecule. In this case, these two particles can be the same or they can be different, and I'll show you what I mean by that in a moment. The main key to focus on here, though, is that we have two polar compounds. If we have one that's polar and another one that's polar, then that means that we're going to have some sort of dipole-dipole interaction between them. Now again, those can be the same or they can be different. So I'm going to model that with this oval shape with a positive and a negative, and the second compound is going to have an oval shape with a positive and a negative. So as you can see right now, you can't see the difference between these two. That would tell me that these are the same particle. But if I colored one yellow, now you would say, oh, those two are two different things. One is colorless, one is yellow. So that tells me that those are different substances. That's how I can say that this could be the same particles or two different particles. So let's see what happens when these mix together. I'm going to start by modeling this with a pure substance. So let's say I have phosphorus monofluoride. And so I'm just going to put here a oval with a positive and a negative, and with it I'm going to have another phosphorus monofluoride, and that's going to have another positive and a negative, and then they're just going to stack on top of each other like this, and you will see that we have all of them stacking on top of each other with the positive and the negative interacting with each other and completely surrounding each other. So you'll notice that each negative is surrounded by a bunch of positives, and each positive is of course surrounded by a bunch of negatives. So this is an example of a dipole-dipole interaction of a pure substance. Everything in here is the same, and this is a pure substance. Now what happens if I do a different substance? Let's look at this one. Let's try nitrogen monofluoride. The end that's more positive is the nitrogen, the one that's more negative is the fluorine, and so we see a positive and a negative, and then we're going to have a whole bunch of those, and we're going to put them all together. So positive, negative, we just draw them all in, and again we're going to see that all the positives are surrounded by negatives, and all the negatives are surrounded by positives, and so we have a pure substance that has dipole-dipole interactions. When we mix these two together, we're still going to have dipole-dipole interactions because the two substances are both polar. First we have phosphorus monofluoride, again polar with a positive and a negative, and then we're going to add to that the nitrogen monofluoride, again a positive and a negative. We're just going to mix those up. This does not have to be an equal mixture, so I might have a whole bunch of the phosphorus monofluoride and a few of the nitrogen monofluorides, or we might have a lot of nitrogen monofluorides. This will vary. Again, mixtures can vary, but we can see that they're going to be a mixture of two different substances. And yet the interaction will be a dipole-dipole interaction. Now let's go back to the hydrogen bond, which is a type of dipole-dipole interaction, but it's really, really strong. So again, a hydrogen bond is a very, very strong dipole-dipole interaction. It is super strong because the molecules are very polar, because we have something that is the least electronegative atom, that is a nonmetal, and that's hydrogen, and it's bonded to the ones that are the most electronegative, nitrogen, oxygen, or fluorine. Now I'm going to consistently say fluorine, oxygen, or nitrogen, and that's because I like to remember it as a kind of an acronym, and that is, I like to say when hydrogen is on the phone, it has a really strong interaction. Phone being fluorine, oxygen, or nitrogen. So that's just my way of speaking. Hopefully it'll help you out so you remember which ones the hydrogen has to be on, fluorine, oxygen, or nitrogen, and it's going to bond to another fluorine, oxygen, or nitrogen. So it only happens that we get a hydrogen bond when both species have fluorine, oxygen, nitrogen, and then one of them has to have hydrogen on attached to the fluorine, oxygen, or nitrogen. So I'm going to use HF as our example. We have an H and an F. Again, these are very polarized, with the hydrogen being the most positive and the fluorine being the more negative one. And again, we're going to model that with a oval with a positive and a negative, and then we're going to put another HF in, and it's going to again be a positive and a negative, and we'll see that all of these ovals line up so that all of the negative charges are surrounded by positive charges, and all of the positive charges are surrounded by negative charges. And what we see again is that these can be the same molecule. In this case, all of them are HF, or we could mix it with something else that has a fluorine, oxygen, or nitrogen and is polar. It does not have to have a hydrogen on it, although usually we're going to see that they do because it tends to bond the best. So we could put in, let's say, NH3. So NH3 and HF mix well with each other because they both have the ability to hydrogen bond. There's NH, and again, this is going to be polar, and I'm just going to model it with an oval, even though it's not exactly correct. We know that one end is more positive, one end is more negative, and we're going to bind that with our HF and see how they mix together. And again, we'll see that they can mix together, so this would be a mixture that has hydrogen bonding present. Remember, we still have covalent bonds within the compound itself. That is an intra-particle force, but the strongest interparticle force in this case is a hydrogen bond. It also has dipole-dipole bonds. Again, those are lower in energy. They're going to be present, but we're going to say the strongest one available is the hydrogen bond, and that's because we have fluorine, oxygen, or nitrogen. One of them has a hydrogen attached to it. That's the minimum. At least one has to have a hydrogen on the fluorine, oxygen, or nitrogen, and the other one has to have a fluorine, oxygen, or nitrogen present and be polar. Now the next one isn't a very good one, but it does happen. It's called the dipole-induced dipole. This is an attraction between a polar substance and a non-polar molecule. To model the polar molecule, we're going to do our usual oval with a positive and a negative, and to model our non-polar, we're just going to do an oval, but it won't have the positive and a negative in it. In this case, we have something that is polar and something that is non-polar. This must be a mixture. It cannot be a pure substance because I cannot have something that is polar be nonpolar. It's either polar or nonpolar. It can't be both at the same time. So we know that this is a mixture of two different substances. One's polar, one's nonpolar. These two really don't mix very well. It's a fairly weak interaction. We see that the polar compound would prefer to have its dipole-dipole interaction that it normally has with itself, and the nonpolar one likes to be with itself. So they tend to make a layer, but if you see like oil and water, one is polar, one is nonpolar. They don't mix, but they do come in contact with each other, and when they come in contact, they're going to have a dipole-induced dipole interaction, which is definitely weaker than your dipole-dipole interaction. So at this point, the dipole part of it should make sense. Because one atom is more electronegative than the other, we know that the electrons are flowing towards one side more than the other, and therefore the compound is polar. But what about the induced dipole? What does that mean? Well, induced means something that is causing or being caused by something else. So what we're going to do is we're going to put this polar compound next to something that is nonpolar. And what's going to happen is you notice that there's a negative off to this side, but that's right next to this nonpolar compound. When you look at the nonpolar compound, what it sees is a negative charge right next to it. And so because that negative area has extra electrons, the electrons, as they're running around this molecule, remember they're being shared between the two atoms, as it's running around, it runs away from that negative charge. So the electron tries to get away from that negative charge. And that's going to come into another polar compound that might have a positive on that's closest to it, and so it'll be attracted towards that positive. And we see that there is an induced dipole where originally there was no polarity at all here. What we see is that because there's a positive on one side and a negative on the other side, the electron runs away from the negative and towards the positive, and it induces the polarity. Again, no polarity by itself, polarity when it's near something polar. Now, this doesn't have to have a positive and a negative on each side of it. As long as one of them is present, it's enough to make it induce the polarity, which is what we see at the border of oil and water. So we see that the water is polar, and it'll attract parts of this nonpolar oil. And our last force, the weakest one that we're going to look at, will also be using this induced polarity. And that weakest force is called London forces. In our book, it's also called dispersion forces, and often you'll hear it called London dispersion forces. I like to call it induced dipole, because in this case we have two things that are nonpolar. So they both have to be nonpolar. Those nonpolar substances can be the same or they can be different. For example, we could have a molecule of chlorine bonded to a molecule of chlorine. Those would be the same, which means it would be a pure substance made up of molecules. Or we could have that same chlorine bonded to a bromine, which is a different substance that is also nonpolar, and those two would also have London dispersion forces. But of course that would be a mixture. So how do these forces work? In our previous example, we noted that in the induced dipole, what was happening is the electron was going from one end to the other. Now notice that that electron is running around these molecules. So it's running around and around. At any one point in time, the electron is off to one end. As it comes off to one end, there is a partial negative charge that is in that position, and the other end will be partially positive. So we see that there is an induced dipole, but it is only there for parts of a second. What's happening is the electron is over to this end for a second, and then it goes back to the other end. But in that instant, while it is off to one side, it's going to look at the neighbor atom, and it's going to force the electrons away from that end on the neighbor atom. So it will induce a dipole on the neighbor. And then that one says, oh, my electrons have run off to this side, and its neighbor does the same thing. And so throughout the system, the electrons are sort of flowing together, and they're all becoming slightly induced dipoles. Now again, this is happening super rapidly, and there's nothing causing one to do it more than the other, but they sort of synchronize, and you'll see that there is some minor attraction. And these are called London dispersion forces, where there's an attraction between two nonpolar molecules, and they're attracted by this induced dipole, inducing the neighbor's dipole, inducing the neighbor's dipole, and continuing on. And as soon as those electrons run the other direction, you'll see that now there's a positive on that end, and the neighboring one will become positive, and then it'll just continue down the line. And so that's how we get London dispersion forces.